Hi, my name is Sam Latshaw, and I'll be talking about the development of energy storage. One of the earliest forms of energy storage is the flywheel. The form of energy a flywheel stores is kinetic energy. It does this by spinning the mass of the wheel at high velocities. A motor and a generator is attached to the flywheel. The motor allows the user to charge the flywheel by spinning it using electrical energy, and the generator allows the user to, when it's time, convert the rotational energy provided by the flywheel to electrical energy. The main use of a flywheel is to provide continuous power when the energy input is sporadic and not constant. The flywheel's first seen use was around 3000 BCE. It was used on a partisan wheel to provide continuous and steady rotation when the user pushed on the pedal. The flywheel is also seen on a steam engine. It stores the energy provided by the piston firing. Flywheels are useful for many different reasons. They have a high power density, high conservation efficiency, a long lifespan, a low maintenance cost, and they are environmentally friendly. They're also a lot faster to charge up than other energy storage methods. There are a few drawbacks to flywheel energy storage. The first is that they have a small capacity compared to other energy storage methods. Another drawback to flywheel energy storage is their high power loss. They can lose up to 3 to 20% of their power every hour depending on what materials they are made from and what environments they spin in. To combat the high power loss, highly efficient flywheels operate in a high vacuum environment and they have magnetic bearings. This reduces the amount of energy lost due to friction. One of the more recent applications of flywheel energy storage includes using them in regenerative brakes. Flywheels have also been used in space, where they act not only as an energy storage method, but also as a gyroscope to stabilize the space station. A more recently invented and more widely used form of energy storage is the battery. The battery was invented in the year 1800 by a man named Alessandro Volta, the man in which the unit for electrical potential, volts, was named after. It stores energy by creating an electrical chemical gradient. The battery consists of three parts: electrodes, an anode and a cathode, an electrolyte, and a separator. The cathode is connected to the positively charged electrolyte, and the anode is on the other side of the battery, separated by the separator. When the anode and the cathode are connected through a wire, a current runs through the wire due to the difference in electrical potential. The most commonly used current flow model used today is conventional current flow, where the current flows from the higher potential to the lower potential. However, electrons actually flow from lower potential to higher potential. Some common batteries and their materials listed in the order cathode, anode, and electrolyte include a car battery that uses lead, metallic lead, and sulfuric acid, an alkaline battery which uses magnesium dioxide, zinc, and aqueous potassium hydroxide, and a laptop battery or lithium-ion battery which uses lithium cobalt oxide, graphite, and lithium hexafluorophosphate. Some major differences in these types of batteries are their power output, their power loss, and their rechargeability. The major advantage to batteries over flywheels is their ability to hold energy. Nickel batteries degrade 10 to 15% in the first 24 hours, and then 10 to 15% every month after that. Lithium-based batteries only degrade 5% in the first 24 hours, and then 1 to 2% every month after that. Compared to flywheels, 3 to 20% every hour is very minimal. A more advanced energy storage method that could be used in the future is superconducting magnetic energy storage, or SMES. SMES stores energy by creating a magnetic field from the cryogenically cooled superconducting magnet and coil. It consists of three parts: the superconducting coil, the power conditioning system, and cryogenically cooled refrigerator. The superconducting magnet part of SMES was discovered in 1955. There are some incredible properties to SMES. First of all, the energy inside of SMES does not degrade when cooled below a specific point, so theoretically, the energy can be stored forever. Also, the total efficiency described as the energy in divided by the energy out is around 95%. The main reason why SMES isn't used today is that the superconducting magnet and coil need to stay around 4 degrees Kelvin to be ideal, and this requires a ton of energy. Also, superconducting wire costs a lot currently. Currently, one of their only uses is to increase the reliability of a power grid. That was my video. These are my sources, and thank you guys for watching.